This is one of the tallest buildings in Boston, 60 stories of mirrored glass, designed by one of the most respected architectural firms of the 20th century. In January 1973, during a winter storm with 75-mile-per-hour winds, large glass panels began falling off this building. Each pane weighed around 230 kilograms. 500 pounds, heavy enough to do real damage to anything below. The problem ran on for many years. By the time it was resolved, all 10,344 windows panes on the building had been replaced. For months on end, sections of the tower were patched with sheets of plywood painted black. The city nicknamed it the Plywood Palace. The glass did not fall because of the bad manufacturing alone. It fell because the insulating glass units were built with a rigid internal bond between the metal spacer, reflective coating, and the glass. This bond could not accommodate normal differential movement. The aluminum expands at different rates from the glass. Wind flex adds to the thermal flex. When the bond between them is too stiff, stress concentrates at the edges of the glass. Microscopic cracks form, and windstorm pushes them past the point of fracture. My name is Eugene Korch. I practice and teach facade engineering, and today we are talking about movement and tolerances. Here is something that surprises a lot of people. Every building moves every single day. The sun hits the surface in the morning and it expands. At night it cools down and contracts. Wind pushes the top of the building sideways. Floor slabs deflect under the weight of people and furniture. Concrete slowly creeps under load for years after it is cast. All of these things happen constantly and at the same time, not one after another. None of these movements are large. A 3-meter aluminum mullion might change length by 5 or 6 millimeters over a year. A floor slab might deflect by 10 to 15 millimeters under load. These are small numbers, but if the joint at the end of that mullion was designed with only 8 millimeters of clearance, 5 millimeters of thermal movement does not leave much room for anything else. And that is before we even talk about tolerances. If thermal expansion goes one way and the slab deflection goes the same way, the effects add up. If several movements stack in the same direction at the same moment, the combined effect can be much larger than any single one. That is the real challenge. Not any one movement on its own, but the combination. Now let's talk about the other half of the problem. Tolerances. This is something most people outside facade engineering have never thought about. Imagine having a niche in the wall exactly 1 meter wide. You order a bookshelf to fit in a 995 millimeters to leave a small gap. At the factory, the shelf comes slightly wider than intended, 997. On site, the niche is built slightly narrower, 996. Each deviation is within the allowed range. Nobody made a mistake. But together, the shelf does not fit. On the facade, the same thing happens with 4 or 5 components in the chain instead of 2. The structure is slightly closer to the facade line than the drawing shows. The frame is slightly wider. The glass is slightly bigger. The installer is off by a couple of millimeters. Each one is within the rules. But if they all go in the same direction, your 7 millimeter gaps around the glass disappears completely, and you still need that gap for thermal expansion. This is the most dangerous thing in facade engineering, because formally nobody has done anything wrong. Everyone worked within their tolerances, and yet the gap is gone. When the movement and tolerances are not properly accounted for, the facade tells you, sometimes loudly. Let me show you a few examples. A dark metal panels fixed at all 4 corners without any room to expand buckle visibly when the sun hits them. This is called oil canning. The panel is trying to grow, but it has nowhere to go, so it distorts. It is not a structural problem. The panel is not going to fall off, but it looks horrible, and on a building where appearance matters, and that's all buildings, it is a serious defect. The fix is simple. One fixed point and let the rest of the panel slide freely. An example of the fixed point is a hole in the panel with the same diameter as the fixing going through it. No movement at all. An example of the sliding point is an oversized hole or a slot, and the fixing sits inside it with the room to slide as the panel expands. One fixed corner anchors the panel in space. The other 3 corners are oversized holes. Let it grow and shrink without forcing the load anywhere. The expansion goes somewhere, the panel stays flat. Insulated render is another classic victim. It is rigid and brittle. When the structure behind it moves, the render cannot follow. It cracks, almost always in the same places. Corners of the windows, junctions between different materials, at floor levels where the slab deflects. Once it cracks, water gets behind it and the real damage begins. The insulation gets wet, the adhesion deteriorates, and in severe cases, whole section can debond and fall away. The solution is simple. Movement joints in the render at the design stage. After the render is applied, there is no good fix. And here is the one that nobody expects. A facade that looks perfect, no cracks, no leaks, no visible damage at all, but it makes noises. Clicking sounds in the morning when the sun hits it, and something like a small metal ball rolling inside the wall in the evenings as it cools down. Residents complain, maintenance inspects, finds nothing wrong. The cause is almost always thermal expansion that was not properly accounted for. Metal surfaces that should slide smoothly against each other are sticking and releasing in small jerks. The sound travels through the structure into the apartment, and here's the problem. Once the building is finished and occupied, this is almost impossible to fix. You would have to take apart the connections and redesign them. On an occupied building, that is not realistic. Sliding doors give us another way to see this. Imagining a balcony with a sliding door installed on the slab edge. The door is rated for a maximum frame deflection of 10 millimeters. Then someone moves in a piano, or a jacuzzi, or hosts a party of 15 people standing near the door. The life load at the slab edge pushes the deflection up to 15 millimeters. The frame warps. The sliding mechanism jams. The door will not open or close. No bracket has failed, no glass has broken, but the building owner now has a door that does not work, and the cause is buried in numbers that were never compared. And here's one more. A stick curtain wall where each mullion and transom is installed individually on site. The slab below deflects, the frame follows the deflection, the glass inside the aperture created by the mullion and transoms rotates slightly. The pressure plates still hold it, the glass is not going anywhere, but the rotation opens small gaps between the gaskets and the glass. Air gets through, water gets through. The wall has not failed structurally, it has failed in performance. And that is the hardest to diagnose because everything looks fine from the outside. This is a 10-minute video and we have only scratched the surface. If you want the full picture, every type of movement explained, how different facade systems handle it, joint design, brackets design, real project examples, and the coordination process between the facade engineer and the structural engineer, we run a detailed technical webinar that covers all of it, with dozens of diagrams, animations, and practical guidance. The link is in the description. If there's one thing to take away from this video, it is this. The facade engineer cannot do this job without one document. It is called the Movement and Tolerances Report. It comes from structural engineer, and it tells you how much every point of the structure moves under every type of load, how much the slab deflects, how much the building sways in the wind, and how much the columns shorten over time. Without these numbers, the facade engineering is guessing. With this document, every joint can be sized correctly, every bracket can be designed for the right range of adjustment, and every connection can be checked against the worst-case scenario. The brackets that hold the facade to the structure are designed with slotted holes and adjustment plates, typically to allow plus or minus 25 millimeters of adjustment in 3 directions. Without the movement data, you do not know how much adjustment you actually need. And here's the key question that this document lets you answer. For every joint, every connection, and every panel on the facade, what is the worst combination of movement and tolerances that can occur at this point? And have we designed for it? If the answer is yes, the facade will perform. If the answer is no, or if nobody even have asked that question, that is where the problems begin. Let me bring it back to where we started. A 60-story tower in Boston, built with most advanced reflective glazing of its time. Every single one of the 10,344 window panels had to be replaced because the glazing units were assembled with a rigid internal bond that could not accommodate the differential movement between their layers. The way the glass was bonded and the way the units sat in the wall could not handle what the building and the weather naturally do. That building is still standing today, but the recovery took years of work and millions of costs, all because one aspect of facade design was not properly addressed at the start. And if you want to go deeper, the full course with lectures, animations, and live webinar is in the link below. I will see you there.